Okay, so it comes with a couple of things in it that aren't okay with the OpenGL, whatever it is. I'm going to fix one of the things too. So you might have been doing OpenGL stuff, and it hasn't been highlighting GLSL for you. You can highlight GLSL if you want to. So it varies by editor. So for most of them, you can do something kind of similar to what you can for Vim. So maybe I'll just make it work, and then I'll show you how it works. Okay. It is .vim. .vim dot. Okay. So if we go to .vim, it's got all these directories in it. Most editors and IDEs and everything are set up similar to this. And I'll have some scripts or some directories like this ft-detect. This is a file type detect. And so if we look at GLSL, I went online and I typed, Vim GLSL syntax highlighting. And what I got back was these plugins here. Extensions supported by Chronos Reference Compiler, etc. And it's got a maintainer up there. Not quite sure how to say his name, but he seems to have done a decent job. So he's looking for files with these indies. And then for syntax, again, same thing, same maintainer. And so he's got the kind of a definition here of what matches what. What does a number look like in this language? How do you tell if the swizzle has happened on a vector, and what are some words that are important here, and all that kind of stuff. And so then once that's set up, there's also an indent file, and so this just explains standard indentation options for it. Now that said, I have my indentation options set for Vim on the whole system somewhere else too. So now that's set. You can see it's syntax highlighted. And I'll keep track of it. Okay, so anyway, similar procedure, just depends on your editor. Okay, so attribute is replaced by in, and so that happens in both of these. And in varying is an out. Uniform stays the same. And that should be a complete update to OpenGL 4.5. Pretty minimal. For the fragment shader, this has to be an in. And we have to declare this GL frag color as the output. Is it vec4? Okay, so that should be an update to OpenGL 4.5 again. So now everything works. Good. I didn't show you that it didn't work before we updated it. That didn't sound very interesting. Okay, instance rendering. So if we look at this cube.cpp and take a look at how these things are done. Couple of things. If we're going to duplicate the cube, we're going to have to take a step back. If you look at the cube here, we're pretty close. If we put a second one, like over here or something, maybe we'll see the edge of it. It can really help if we just take a step back. Okay, so step back comes in this whole mess right here, and it has to do with this view line right here with the GLM : GLU look at. GLU look at here is the same thing as GLU look at on OpenGL 1 point whatever. That is, lets you set your viewing position and what you're looking at and what up is like to you. In case you're like an airplane in a banked turn, or you just died and you're laying on the floor, or something like that. Step back here just means this is our position, and so if we step down the z-axis a ways, say position 8, then that should take care of that. Now we can still be looking in the same direction. The rest that's fine. Okay, so let's set up our, let's take a look at that real quick. I don't know where we went, but it definitely wasn't a good spot. So what if we do, if we do -8, that doesn't help us. I'm surprised that didn't work because I did the same thing like 10 minutes ago, and it worked. Another make? No, it's just truly gone. Oh, flip plane. That's it. So we stepped 8 units back, and we're clipping things at 10. It seems like that should be okay, but my guess is for some reason it's not. There we go. Cool. Okay, the lines there, I've been meaning to kind of review these at some point. The model view matrix, so the animation matrix here adds our animation. That one's actually applied last. These are applied in reverse order. The model view matrix moves our model around where we want it. The view matrix sets up where we're looking from, and then the projection matrix sets up the way the projection looks like in terms of viewing angle and are we a cat or a rabbit and all that kind of stuff. And so anyway, that comes together into this matrix, this model view and projection matrix, MVP, and it's got the animation tacked on there, so maybe it should be MVPA. But that's how we set that stuff up. Okay, so instance rendering. So we take a look at this cube thing here. Right now it draws everything here. So if we wanted to make a mess of our program, then we could go ahead and duplicate main. If we wanted to draw it somewhere else, we could just take this apart a little bit and say add something on it. There's our course 3D.y. If we add on a vec3 of say 0, let's add something on an x, like 3 in x, nothing in the other two. Then we'll have our, let's put it over to the side. We can go ahead and see if that works. We just comment out that one. It's over to the side. Yeah, you can see it's off-centered there. So we've successfully made it move. But we wanted to draw both of these things. And since this is a vertex shader and not a geometry shader, we can't just say, like, emit vertex here and emit both of them from one run of this vertex shader. Let's bring you up to date with the vertex shader.
Oh, that's
so since we can't say that in the vertex shader, we're left without as good of an option to do this. So here's one. What we'll do is we'll key this off the instance ID. So if DL instance ID equals 0, we'll do that. Else, we'll do that. And then we'll go ahead and leave the color alone. So the color comes through the same in both instances. So that's instancing, but it's not going to have any effect yet. If we run it, it runs fine. It doesn't care about our instance lines, but the only instance is instance 0. So we have to modify that a little bit. And that's in cube.cpp. So down here on, right now we're calling draw elements right here. So the actual drawing part of this, we're needing to kind of review this one too. We go ahead and clear everything and set our program to be used and our vertex attribute array, which is actually where our coordinates are stored. You can see it's attribute coord 3D. And we go ahead and bind that and make it current. And we say that we've got a pointer to that array. And so we're actually going to enable a second one. So we do this twice. The other one's for colors. Same sequence. Go ahead and enable the colors as another attribute. And so then we have to bind the buffer that has the elements in it because the elements are different than the vertices here. The cube is drawn by with recycling the vertices. There's vertices up there. And then down here we've got, this is vertex 0, vertex 1, vertex 2 for that triangle. And the authors of this file, you don't have to divide it into lines like this and say front, top, back, bottom, right, etc. You just put it all in one line if you like, pain and suffering. But they hit enter after every 3 so that each of those 3 represents one vertex, or one triangle. And so there's a triangle on the back between vertex 7, 0, 1, 2, 3, I guess that's the last one, 7 and 6 and 5, connecting those 3. So down here in the drawing, we have to bind that buffer, get it ready to use. And once we have finished dealing with that buffer, we can finally call GL draw elements. And so draw elements as opposed to GL draw arrays. GL draw elements uses these already bound buffers, or already enabled and set of attribute arrays, and uses each of the elements that we've given it that we bound right there, and goes ahead and makes it. But it doesn't give us actual instances. It just gives us one instance. So if we look at this one, man GL draw elements, it's got the explanation of all the parameters here, but then down at the bottom, it's got a note. You can also call GL draw elements instanced, and that's what we want. Okay. Okay, if we were made a time, we'd pull them both up, and I'd show you that the parameters are identical. until we get to this GL size I prim count, or however you're supposed to say that. Anyway, what it does though is specifies the number of instances of the specified range of indices to be rendered. Okay, so that's our number of instances, basically. It says it in a really confusing way in this man page. So that's your number of instances right there. Okay, we'll just go ahead and make 2 instances. And then we have to rebuild this because we made a source code change. And we have to change this to be actually GL draw elements instance. Since the edit function there wasn't okay. And there we go. We got 2 of them. Whoa, without a geometry shader. So the advantage here, the geometry shader runs once per primitive, and so it can limit our parallelism a little bit. We're still doing this in a vertex shader, so it's still running once per vertex, and except now it's running twice per vertex. Yeah. So is it better to make a whole bunch of identical objects than like drawing each one of them individually, or should you just draw one of them and have the shader control where they all go? The latter would be better. See, so the way we did this in game engine design, we basically called this line once for every object we wanted to draw. And so if it had the same visuals associated with it, we just called this once per location we wanted it to appear. And the problem there is, suppose your object is, if your object is really complicated, that's fine. But if your object is simple, say it's only got like 100 vertices and you've got, like, say, 2,000 shaders, you're only keeping 100 shaders busy at once. Doing the whole serial. So we should draw the walls on the graphics card. Yeah. One wall that we base everything on. Exactly. And so what you have to do is put a buffer into memory that has locations of all the wall panels, and then call draw elements indexed with the number of instances, 1 per wall panel, and then have that be indexed into the buffer that holds all the locations of the wall panels. Oh, I have to remember to do that. Yeah, it'll make it a lot faster. That's one thing that OpenGL, greater than 2.0 deals with much better than previous ways. Greater than, not equal to. And you can actually, if you say moving all the walls, you can use transform feedback to move all the walls on the GPU, and then continue to draw that array of walls later. So, is it better to draw to make a single wall segment and then do it this way on it, or is it better make a single display list out of all of your walls in place and draw that? Well, if you're using OpenGL that's recent, the answer is not the display list, because that's been deprecated for a good while. Well, equivalent. But the display list was the previous way that you would do something like that. The old mechanism for this. Yeah. That's good. Yeah. The thing about the display list is the display list kind of saves, it records a series of actions. And so if you took your object and drew it in a whole bunch of places and recorded that all in a display list, then you can run the display list without consulting the CPU for each thing, which is great, but it's not quite the same as telling the video card, okay, we're going to go ahead and draw 200 wall panels, and here's your array locations, and off we go. Okay, so let's talk about the project. I think we're high enough that it's time. So actually we're at 7 out of 10. That's not that bad, especially considering the time of year. Okay, so last time I mentioned that you got your project of sufficient complexity, whatever in the world that is. And so I promised to try to define sufficient a little bit better. So here's my attempt. So for the project, you have a list of features, and probably if you think of an idea, I want to make a scene that's a battle between good robots and bad robots shooting each other with lasers, and the robots are going to be shiny, and the lasers are going to partially reflect. And you're going to end up with too complicated a feature list really, really fast. So I'm guessing that most ideas people think of are going to require paring down, not the other way. So they'll have to come with sufficient complexity and some sort of a feature list for it. They need to not use gross inefficiency. So if you're specifying all the vertices on the CPU every time, then it's really not taking advantage of the video card. So it's got to avoid that. Now, I said no gross efficiency here because things can always be optimized better. When you have it working, you might be like, okay, the card is doing all the work. This is pretty efficient. And then you show it to somebody who's been a game programmer, and they're like, wait a minute, you're doing a floating point multiplication here. You could have just treated this as an integer and done a bit shift, and it would have done the same thing. You don't have to find all that kind of stuff. Nobody ever knows when they found the last one of those things either. So it doesn't have to be perfectly optimized. It just has to avoid things that are blatantly bad. So then, as far as how to grade it, basically I'll grade by a fraction of a complete. However, it might be that you put together a feature list that's really way too optimistic in one way or another. So as long as the new feature list would have been acceptable in the first place, you can change the feature list later. It also means that if you get to it and you're doing this and you're like, well, I really don't like this particular feature, I'd rather do something else instead, you can revise it to explain more what you actually did. Don't want this to be something where people are too locked into something where they're like, this idea seemed great, and now it just seems like it's not as great. So that's the plan there. I'll talk about due dates in a minute. Let's go over the examples real quick. So I came up with a few examples, and I don't know if these are necessarily exciting or not. Just thinking of examples. Here's kind of the project description format here. So it has a title. The first one's just a grass field that has a lawnmower that will come by later. And so that's the idea. And I was not using the Windows XP background when I thought of this idea. That's not where it came from. In fact, I was actually visualizing it as flat without any cows. So the plan here is, you gotta have this grass, and you gotta have a lot of grass. One of the features is you have 100,000 blades of grass, and these cards can totally render 100,000 blades of grass. It's not a problem there, as long as you're not having the CPU do every bit of it. You have all this grass, and it gets blown around by some breeze. We did that earlier. You varied in color, and so one way to do that is just have the grass stalk change as it goes and have some degree of randomness. And grass is oftentimes a little bit tanner or a little bit greener. So then weeds. So weeds. The whole time I was doing this, I was just imagining a tree that we've already been doing, just at a kind of lowish level, making a weed. But some kind of other plant that grows up with some random chance when you lay the whole thing out. They'll be taller than the grass scoots so you can see them. So then the lawnmower will be a textured box with wheels, which is a pretty simplistic lawnmower. It's like the refrigerator crate lawnmower that has wheels. So it moves along the grass, and the wheels will turn at the right speed. And that's a pretty good trick, because you'll have the grass here, and so then you got the wheel on the lawnmower, and so you can't stick them together. They're not stuck. They only look like that. And so you got to call georotate to rotate this at the right speed, that it doesn't look like it's moving too fast or too slow. A common thing that happens in rendering, both in games and movies that have been hastily produced, is that when animated characters walk, their feet actually don't walk at the same rate as they move. It looks super goofy. You're always like, man, they must be so concerned about falling over right now. Looks like they're walking on a floor that's made of ice with oil poured on top, and yet they're somehow standing there. So anyway, with a wheel though, it's much easier than walking. Walking is difficult because the dynamics are just complicated. With a wheel, all it is. Okay, and actually everybody in game engine design did something with rolling spheres at the correct rate last fall. And it was hard not to make projects here that would give everybody who survived game design an advantage. But, did the best. Except for one of them. Okay, suggested project 2, a fireworks show. So the idea is the shells get launched. It's just shells. You don't have to worry about like brown bloom flowers and smoke bombs and kids running around waving sparklers and all that other sort of thing. That would be a very different project. So the shells will have an angle and a speed and a delay before bursting, and so maybe they're launched with a random one. Maybe there's some kind of pattern. It doesn't really specify in here. And then they burst into a number of particles, and so they burst in different ways. If you go to everybody goes to fireworks shows. What I'm talking about. If you go watch fireworks, they have a variety of different effects. For example, you can have the particles come out quickly, and burn out before there's a tremendous amount of effect from gravity, or you can have them stay on fire for quite a lot longer, especially popular if it's not over dry grass in the summer. Anyway, think of 5 different effects and 5 different color patterns, and so for each effect, they can each have each of the color patterns yielding 25 types of shell. So that actually gives a pretty decent variety. So then the shells and the particles will both be subject to gravity, and the GPU will be used for physics calculations for the particles. Specifically omitted shells there. It might make it a hassle, and it probably isn't necessary because there's not going to be very many of them. Now, if you want, now it doesn't say that they're not on the GPU either, and so the shell calculations can be really wherever. The camera will primarily remain at a safe viewing distance, but every 10 seconds it'll go fly through the show and assume a different viewing position, like you're some sort of insane bird thing that's watching it, and it occasionally flies through it. Both of these have a midpoint defined. So the midpoint here on that one is simple. Midpoint on here is that the shells launch and explode into token effects that don't have any particles. Like it explodes and it becomes a bigger sphere for a moment, and that's that. And so that means getting a lot of the base of everything together and working, but leaves a lot of work for later. I thought that maybe people who took 492 might be interested in doing an update so that the game engine uses OpenGL 4, preferably in kind of a competent way. This doesn't necessarily mean starting with the class game engine, which is a little bit tied to the 1 point whatever branch. It could be brought out of the 90s. Anyway, so basically the major thing here would be making all the OpenGL calls check to see if they're OpenGL 4.0. And the answer for most of the OpenGL used in a game engine is no, it's not. So it involved quite a bit of writing shaders and whatnot. So the feature list mostly has to do with visual stuff. Objects that can be stored in vertex buffers in a GPU, although I should say the mesh for the object or the visual part of the object, since these objects have a game engine part of the object too. This checks for collisions and that kind of stuff. Engine will be multi-threaded, yes, of course, they usually are these days. Lighting calculations, of course, have to happen differently, and I haven't talked about them at all yet. Focus on. So the first block of tutorials that we started with in the class, one we keep borrowing from, actually has a lighting arc with basic lighting, and then these ones down here talk about texturing and lighting. And so it's sort of a texturing lighting method I've been intending to cover at some point. That's covered in there, and so yeah, I just use that kind of lighting. And in level of detail will change depending on if things are close or far away. And so this is probably best done on a tessellation shader, which we haven't talked about yet. There we go. So midpoint playable, so you can see stuff. No lighting, no level of detail, and so it's rather easier there. So I kind of intend to finish this class demo project that we finished around half of or so. And so it has a fruit tree that's generated, and has fruit on the end of it, and then it'll explode. And so the fruit will be all thrown into the air. And so we'll have at least 500 fruits, and I actually intend to put more fruits in it than that. I think it'll support quite a lot if it needs to. Or it could be a whole orchard of exploding fruit trees. Who knows? Anyway, it should definitely support that many. And they'll all have some sort of trajectory, but then they'll have particle physics, kind of like the fireworks show, except it's the fruit flying show. And then the fruit will also have level of detail. So if you go up and look at the fruit up close, it'll look good, and not if you come back. That was my intent for something to demonstrate tessellation shaders with. Is take one fruit separately and then just have the level of detail thing. And I've been kind of mentally penciling this in for next week, but this class is just kind of generated on the fly. I don't ever quite know what's happening a week ahead. So that's the plan there. Okay, so midpoint on that. It's kind of a few of those fruit falls straight down. So that's some examples of what I think a decent project might be. So then we need due dates. And so this is where I wanted to just kind of talk to everybody and get everybody's feedback on it, and we can kind of work out this in a somewhat democratic manner. guided democracy. Okay, so I have been figuring out a calendar here, everybody to present their graphics projects and show everybody how nice they look up here on the projector. Remember that the projector has awful color compared to the regular screen when you do this. But don't hamstring your project just because you know it's going to be shown on something with awful color. Anyway, so I was picturing a presentation of these on the week of October 22nd, so that'd be the 22nd and 24th. I don't know that it'll take the whole time, but it's okay. The class is way behind schedule. If this all fits into one day, then we'll just catch up a bit on the other day. That would be after the midterm. I figure that you probably would want to at least get to the midpoint before the midterm so that you can answer all the midterm questions correctly. And then get a good score, and it'll save you a whole bunch of time too. So that's the plan there. Right now we're in this week here, the week of September 17th. So dates. We got these three here to put on there: project description, midpoint, final version. Description, midpoint, final. Okay. So, when are other things due in classes that Nina or Charles are teaching that I don't know about? Dates of significance.
They don't really have any projects in the classes right now. It's just labs.
Okay.
So you're probably fine. I have a project on November 9th, but it's not.
Okay, that's a good ways away too. Okay. Just want to make sure I'm not plastering some other deadline where everybody's going to be like, we have three things on the same day now. That sounds really, actually like a pretty open schedule. Okay.
Your classes are the ones that have been the ones with the most deadlines.
Okay. Okay.
Oh, yeah, and between all the different ones, like Nina has a quiz every class day and labs, and Charles has a quiz every now and then and labs, and Seth has projects and labs. So between the three of them, Seth has the most.
Okay. I try to front load the classes a little bit. It's hard to do because the class, like this class, you can't assign a great big thing on day one when we haven't had any CPU programming. But that might be what's happening there a little bit. Operating systems is a good one to front load. It's got the C project. So this really can't be any later than the presentation of graphics projects, like October 22, unless that's like a horrible day, but it doesn't sound like it. What are midterms in Nina's class and Charles' class? Week of the 15th.
We don't know anything about them yet.
Yeah, they usually happen all in the same week.
Yeah, that's because midterm grades are due halfway through, and plus the midterm, we go about halfway between here and here.
And usually we don't find out what's going to be fully on Nina's midterm until the weekend before the midterm.
Okay. So you'll have to take care of all that business that week, but then you'll be free of it later. Okay, that doesn't really contradict the 22nd, but I guess for this midterm, well, for this midterm, I mean, obviously the thing isn't written yet, and I haven't thought about it that much, but it's going to talk about 3D concepts, the purposes of the basic types of shaders. It'll probably have a problem where you got like some shader and it's given some vertices and it's like kind of sketch what it prints out. And it'll probably be kind of trivial, like it'll print out like a cube or a smiley face or something. Yeah,
that would be
good one.
Yeah, it'd be hilarious. It's like you're mapping this thing out like a grid. It's like, oh, shit in.
Yeah, and it'll probably have at least one performance question, which either asks, what is a good way to do such and such, or why is the following a bad way to do such and such? I'm not sure which way or what thing exactly.
Plus, we have another hitboxing question.
Well, we're not going to have a hitboxing question because that was a game engine topic, and we haven't been doing collision detection on the GPU, and I don't think we will.
Remember that trig function question time? We're like, all of us had technically right answers.
Okay.
Sitting in a hall with two different math faculty discussing.
yes, that was the octopus one.
Oh, that was fun.
I was the one that they both agreed though had the most correct of the answers.
I mean, I thought it was great because we had,
All all
the two math faculty and Sept.
What's the debate
Oh, yeah.
on what's best?
Yeah, none of us had thought about it, so we were all just kind of going with random ideas. I guess I must have thought about it a little bit, but I didn't think of that in a question, whatever was asked. So here's just kind of a proposal, if that sounds reasonable. What I'm mostly concerned about is, for a project idea, you gotta think of something creative, and you have like 5 days to do it. Is that too soon?
Who doesn't have an imagination?
Well, we can figure it out in lab too, because September 24th is a lab day.
Okay.
And it should work.
Okay,
Alex will be back tomorrow, so he can contest any of us.
yeah, he can, he can. Okay, we'll put this down, well, yeah, he's also not here. Maybe we should put this in there as a proposal. Everybody come with an idea on Monday, and if we could get everything worked out, we'll just like do this one. That's the one I'm attached to. I want that one to be significantly before, and it sounds like Nina's midterms that week, so it would be kind of nice if it was like before that. And then that sort of pushes this other one up at like the 24th or something. It's a 1 month timetable, so it's,
We've got a month. That's
Yeah.
essentially it. Period. From now till it has to be done, we have
Right.
a month.
okay, yeah. Okay, I'll put that on there. If somebody thinks of some like, this is just a bad idea or whatever, let me know. There's a little bit of time to argue about it, not a whole lot.
So, I do have a question.
Yeah.
Where would like a running animal hit on this scale of like complexity to?
A running,
Running in
yeah.
place or running around a field?
Let's just say running in place for now, like, because that's a lot of functions and stuff that you're gonna have to input just to get like,
Not to mention you
if
have
you're
to
just
have a
gonna have
model.
it like the legs are like straight and stuff and going back and forth. I can imagine, make it run around the field, but if you got like the thing,
If you're using a
bends its
proper,
leg up and like keeps its.
if you're using a proper 3D model, you might be biting off more than you can chew.
It just depends how detailed you want it to be. I mean, if the idea is to model it so it looks really good, the hair movements are exactly in line with the skeletal movements, then it's going to take a long time.
I think we're more talking about just having a skeleton.
If it's a goat running around in a field and you're throwing a bale of hay at it, and it just kind of scoots along the ground, it's like probably not even complicated enough. So what I'd recommend on it is come up with some features that, define it as, looks good enough in some way, skeletal animation contains at least 10 joints or something like that. But don't box it into, looks like photorealistic perfection.
Don't try to make Goat Simulator.
Okay, but I'm gonna make the goat throw its head back and scream every 20 seconds. It's gonna watch this thing run and scream.
Right.
So I have a question.
Yeah.
What if you want to just make a hairy sphere where the hairs have momentum as you move the sphere around?
That could very easily become complicated enough.
And how would you remember where the hairs used to be while generating them based on?
That would be the fun part to figure out.
You might have to keep an array that describes the hairs on the card and then program a compute shader to do the movements on a per hair basis.
Okay, so you probably couldn't generate the hairs in the geometry shader?
You probably could. I'd be a little, well, I'm not sure how your performance would end up being with that approach. It could potentially work. Geometry shaders can totally do geometry amplification. Now, you have to feed them back into a buffer somewhere, and then just switch buffers each time.
Just have
You can do it that way.
Just have two buffers that you flip between.
Part of the reason I think a compute shader might be better is people were doing complicated stuff like that with geometry shaders, and defined compute shaders as a more flexible way to do things that could be hacked with geometry shaders.
So in other words, the geometry shader is the more complicated way to do it.
I wondered if it might end up more complicated than, yeah.
When does the compute shader run in the pipeline?
The compute shader is outside the pipeline.
Oh, hey.
So it runs whenever you want it to. So that's why you could run the compute shader to calculate the locations for everything and then run a fairly simple pipeline to actually draw it.
Oh, that's useful.
Yeah, they are. They allow you a lot more control over what happens in your arrays. Like with the geometry shader, there's no guarantee of order when things come out of the geometry shader because it'll emit vertices, and so you end up with a list of vertices at the end. But with the compute shader, if you have an idea how many are going to go in and out, you can come up with an order and keep everything static. So there's a lot of ways that you can optimize things just because you know things and can express it with the compute shader.
When are we covering compute shaders?
They'll be coming up pretty soon. I can't wait. There's a decent explanation on Chronos Wiki.
Yeah, I'll probably end up learning it on that. But
Yeah.
we're starting.
It's yeah. I mean, they're
Honestly, of all the ones you put up there, I like the description of the firework one
oh yeah.
because it actually sounds like something that would be fun to program.
Oh yeah, I think it would. I actually programmed that in 2D occasionally using like Python or something as a 111 demo, but
I know.
It's not nearly as nice, you know.
I remember the IKEA fireworks.
Yeah.
Fireworks? What's this?
I was launching like chairs or tables or something.
Tables.
Tables.
We were launching tables with that had one leg that was smaller than all the rest of them into the sky, and they exploded.
Oh.
We called them the IKEA fireworks.
Yeah. I didn't add smoke on the fireworks. I was thinking about it when I was doing this, and I was like, nah, that's probably too much work. And in the dark, you can't see the smoke anyway. But if you wanted to do, so suppose we had the new GeForce 20 series, then you could not only do smoke in the dark, but you could have them emit light, and you could have the light affect the smoke, because you could have a ray trace it.
You like bringing that up whenever you can.
I'm kind of excited about it actually, because ray tracing has been this thing where people do it for static graphics for all the time. It's kind of a major leap actually in computer graphics.
Ray tracing is amazing. Who wouldn't want ray tracing?
Yeah. Okay, well, so everybody kind of agree, makes sense? Okay. Same as 492, you know, you get to have input into the project. It's like
That's
a graduate
weird.
class.
Oh, this is our pre-grad class?
Yeah, it kind of is in the manner of a graduate class. When you go to a graduate class, it's much more open-ended, and it's much more directed by what everybody's actually interested in. And usually the calendar is sort of a loose suggestion. It varies a little bit. Some of the graduate classes are cross-listed, and so those are more rigid. Because it'll be like, I think computer security this way. It was cross-listed as 400 or 500 level. If you did 500 level, you had to do heap-based exploits, and you had some other extra stuff to do compared to the 400 level. But it was a harder version of a 400 level class. If you take one that's not cross-listed, it's commonly not that way at all, and it becomes much more free-form.
Interesting.
Yeah. And it depends on which instructor too, especially at the bigger schools. Some of the graduate classes are kind of regimented. WSU had a couple that were, but it also had plenty that weren't. When I was at Western, practically none of them were. I took a compilers class at the graduate level, and I'd already taken an undergraduate level compiler class, and so I ended up having kind of my own independent study on optimizers. You know? It's fun. Okay, so today's actual topic, I actually set up a longer and a shorter topic because I wasn't sure exactly how much time we'd have at the end. And I think we're probably a shorter topic amount of time, and that's just fine. I might do the longer one just kind of as a canned demo later. So we've been doing the rendering here. I kind of went over the vertex specification really quick. And I've been noticing in lab, I think maybe I went a little bit too quick there, which is, you know, you got to start somewhere and be like, okay, now this line draws something. And so it's like, oh yeah, we have this line, it does this. We have this line, it does this. Okay, so going back to this a little bit and the way the cube one works. So the buffers in here, OpenGL buffers, we've been using buffers a number of times, and we've actually got 3 separate buffers just to render this silly little cube. And so the buffers, you know, we got one that holds vertices and one that holds colors here. But we got to generate the buffers and then bind the buffer and then copy data to it right there, which brings everything over into a static draw buffer. Now, we could use any of these for translation feedback if we wanted to. So, for example, if we wanted to move all of these vertices, we could set them up as a translation feedback buffer and put everything in there. Or we could make a second one and move them all to that for permanent modification. Maybe we'll do it in a minute. If not, we'll see. Okay, sort of depends on that. Okay, so we got these, the colors array, which works very similar and sets the colors in different ways. I think that the authors here tried to come up with some sort of blending that was pleasing and leads to a more or less complete RGB spectrum. I also noticed that they avoided using black as a color. I think the cube runs on a black background. No, it runs on a white background. Never mind. Okay, so we've got buffers set up for each of these things, and then we've got this cube elements, and it's actually done exactly the same as the others. All of these are static draws since they're being used for drawing stuff, and we don't intend to change it later. So that's our hint for the vertex shader. So then the other side of that, where all of this stuff comes through, down here, we got kind of a pair of functions here, and I think we butchered one of these things to put them both together. It's done as a two-step process here. On idle, we set up our matrix for where everything goes. That's really the entire point of this function from one end to the other, is set up our model view and projection matrix, MVP. All this thing does. And so then we actually do the drawing down here. And let post redisplay causes on display to be called down here. And so this is kind of a fancy way of just saying down here on display. Go ahead and run it, and it would do basically the same thing right here. The reason that we have it this way is glut post redisplay goes ahead and informs glut that we need to do all the stuff that we do if there's been a redisplay action. And so after we've moved the window and redisplayed it, we normally run on display. And so that will get run at that point. Go through there. There's our clear color. So if we decide, for example, that we enjoy having poles charging on our projector screen, we just do that. And so now it's kind of awful. It's a red background. Okay. So we clear everything, and then we clear a couple of bits here. So the color buffer bit is cleared out, but then we got this depth buffer bit. So depth testing is turned on this whole thing, and I never really turn it off to show you what happens, I don't think. So if we go down here and we fail to enable GL depth test, then we're going to get something that looks funny. Definitely funny. So if you end up with something looking funny like this, it probably means that your depth test has become disabled. Okay, so there it goes. And this is exactly the same as it was last time in game engine design. We GL enabled GL depth test, and we have to tell glut that we're going to be using the depth bit, and then the depth bit is set up here. Now, as far as where they're discarded, so when you get a fragment in the fragment shader, it's been through the rasterizer, which doesn't have to rasterize something you can't see. The rasterizer takes the primitives, triangles, and gives us fragments, and each fragment represents a pixel on the screen. But we can see in our fragment what primitives it was from, and that way we can help decide what color it ought to be. Okay. So the color buffer bit's set there. We go ahead and GL use program. Now, if we didn't do this, it was set up here, and so probably we'd actually be fine most of the time. We might not be fine with the odd frame that's drawn not using the on idle method up there. If we were to resize the window, for example, we would trigger on display one extra time, and that particular time the program wouldn't be enabled. So it's probably a good idea to enable it. The reason we GL use program up here is we're about to set this uniform MVP, and you can't set a uniform on a program unless the program is currently the program in use. And so we go out and find the location on the card and set that. So that's set right down here. So then we got to enable our various vertex attribute arrays. So on here, I don't remember how I installed the documentation on here or not. Start typing man. Did I do that wrong again? I'm skipping a key. Yeah, that's fine. There, I got it right that time. Okay, so we got GL enable vertex attribute array. And so all of these things are actually defined in the manual as long as they're from OpenGL 4 or later. So it's got a whole variety of possibilities here. You can enable or disable vertex attribute arrays or vertex array attributes. And enable the generic vertex attribute array specified by index. And so we got to give it this index. And so the index here, attribute cord 3D, is defined as a global for the program right up at the top. Attribute cord 3D right there. So if we trace back how this thing's used, it's set right here where we GL get attribute location from that program. So if the program didn't have an attribute named that, then we'd have a problem right here. And so it depends on having something in our vertex shader or fragment shader or geometry shader or something that has the name specified in attribute name, which would be this one right up here. And you could simplify this line of code if you wanted to. That's a const char star up there. And so you could just say down here, cord 3D. Instead, it would be fine. The tutorial authors chose not to. I probably would have just put it there. That's that one right there. Okay, so attribute cord 3D is set up right there. And so then, let's see, okay. You notice up here, we went ahead and made that array buffer. And so the attribute cord 3D is going to come from the content here from cube vertices. And we generated a buffer right here, where we had this GLU int VBO cube vertices. But that hasn't come in quite yet. So we got the attribute from the program, and down here, we're going to enable the vertex attribute array from the program that needs their attribute cord 3D. So then after that, we GL bind buffer, and the buffer we bind is VBO cube vertices. So we go VBO cube vertices. Let's delete it when I create things. So it's a GLU int up here, an unsigned int in fact. And so it's set right here, that's where we generate the buffer. Then down here with bind buffers, we bind the buffer. Then we copy everything to it. Note that this GL buffer data here does not say VBO cube vertices anywhere in the call. It's already bound. And so that's the one we're talking about. So then down here, we can go ahead and GL bind buffer, that particular thing. So now that buffer's bound, and we've enabled our vertex attribute array, and this also does a state sort of thing. That's what we're talking about. So we got this GL, actually maybe it doesn't. I'm not sure it does. So then I've got a GL vertex attribute pointer. Okay, so the GL vertex attribute pointer, a whole bunch of parameters here. It's got the index of the generic vertex attribute to be modified. So you can see that's attribute cord 3D. So that's the vertex attribute array that we just enabled, and it's a type GL int. So that's the index of that. Then we have 3. So that's the size, the number of components per generic vertex attribute. Must be 1, 2, 3, or 4. Or it can be even that. Initial value is 4. So the reason that we have 3, we defined all our vertices using 3 coordinates up here. So there's a vertex, 3 coordinates. Down there, 3. Okay. We could have defined our vertices with 2, for example, if we were doing something in 2D. I think the initial couple demos did that. Or we could have 4, and we could use the other coordinate. Really, I guess we could interpret it however we like. I may end up doing something interesting with that with the bush fairly soon. Okay, type of each element, GL float. So you've actually got a bunch of types here you can add. You can have a GL byte, GL unsigned byte, GL short, unsigned short, int, unsigned int. Then you get the floating point types, like float, or you can have GL double, depends on your card hardware, whether it likes it. I'm not sure what a GL half float is exactly, but you can have that, or a float, or, so you got a bunch of options there. Okay, so then normalized, specifies whether fixed point data value should be normalized. Now, we're not using fixed point, we're not using GL fixed, we're using GL float, which is kind of the opposite of fixed, the point floats instead of being fixed. We really kind of want just false there, GL false. Okay, but if you're using GL fixed, you might want to do that, might not. Stride. So this is the offset here between things. So you see it's set to 0 there. Now, the reason we might have it not set to 0 on something. So up here, we define two static arrays. They're just defined right there, we never change them. And they're both defined on the stack. We're using stack memory for each of these things, really all of these things. Now, if we wanted to minimize our number of memory allocations, for example, suppose these things are actually stored as C++ objects, which are allocated and placed on the heap, and we want to call new less times in order to allocate space for them. We could interleave the values if we wanted to. Or interleaving might just plain be handy whenever we're setting things up. Like, think about the tree generator. The tree generator adds all its vertices to this one list. It could be handy just to have one list, allocate once. And then where your coordinates are to describe a branch would be, say, a vertex, then say a color, and then a vertex, and then a color. You have something like that. And so if you did that, if you have these two arrays here interleaved instead of separate, then down here, you might want to use the stride in order to sort that out. So if they're interleaved, we just said stride to 3. You're going to take a vertex, then skip 3 because that's the color, then take another vertex. Could do it. We're not doing it here. We could. And we have the offset of the first element. So suppose what you've decided to do, and this might make a whole bunch of sense, is you say you got a bunch of different possible power-ups in your game. And you just go ahead and put all the vertices for all the power-ups into one array. And then you remember the offset for each of them, and off the array goes to video memory. Now, when you want to render one, you just have to remember where it starts and how many vertices are in it. And so then you can set the start point on it. Or suppose you have some sort of object, and it's going to be partially visible, and later it's going to become completely visible. Say it's first stuck in the ground, and it's really complicated. It's sort of the central focus of the game. You might say, well, we'll just go ahead and put everything in order. The ones on top come last. And so we'll render starting with vertex 10,057, because we don't need to render the ones that are still underground. Then once we move it up, we'll go ahead and render the whole thing. You do that. So there's a number of reasons you might want to set that, but I think 0 is probably the most common setting, and it's certainly what we wanted here. So that's what you have for properties there to set up your vertex attribute pointer. So then we have the second vertex attribute pointer. It's basically the exact same thing. You bind the, you go ahead and enable the one you're after, and bind the buffer, and then set up your vertex attribute pointer with all the variety of information we just went through. So then we got yet another one. We've got to GL bind buffer, and we're going to bind GL element array buffer. Notice both of these are bound as GL array buffer. So let's look at GL bind buffer real quick. Okay, so it has a target and it has a buffer that you're going to bind these things to. So I keep talking about how it's a state machine and you bind it, but there's actually a whole bunch of locations you can bind it to. Here's a list. And so we keep binding things as a GL array buffer, which is used for vertex attributes. And that's kind of about the most common place to bind one, but you got all these other places you can bind it if you want to. And so, for example, we could bind it as a GL draw indirect buffer. Here's what a GL draw indirect buffer is used for. We haven't talked about indirect drawing. Suppose you decide you're going to use a compute shader, and the compute shader is going to figure out a whole bunch of stuff related to what you're actually going to draw. You don't want to pull all that information back onto the CPU and then instruct the GPU how to draw with it. That'd be inefficient. So you have the GPU in the compute shader, set up all the drawing parameters in some spot, and then you go ahead and bind that spot as the GL draw indirect buffer, and then you call GL draw arrays indirect, and it goes and draws everything the way the compute shader determined it ought to have been drawn, without ever bringing it onto the CPU. Anyway, so they've all got purposes like that. We used the transform feedback buffer the other day and pulled everything over on there. Right here though, we're going to bind this as GL element array buffer. GL element array buffer right there. So this is full of vertex array indices. And so they're expected to be indices into the vertex array that we've just gone ahead and set up here. Once we get that set up, that's the cube elements there, we can go ahead and get size. And then we call this one here, GL get buffer parameter IV. These ones. So this one's got a few different things it takes. It's got a target, which specifies the target to which the buffer object is bound for these ones, same kind of table. It's got a buffer here that we're looking at. Buffer next, GL buffer size right there. We're only taking three parameters value. Okay, so it takes the name of the buffer object to query, and then that returns the requested parameter. Okay, what are we requesting here? So, the parameter IV, so size. And then after that, we draw all these elements, GL draw elements instanced, using this thing, size. So, this buffer, this returns information about our buffer. And in a way, this is a little bit of an odd thing to do in this tutorial. GL buffer size, params returns the size of the buffer object measured in bytes. We're getting GL element array buffer, GL buffer size, and that's how many bytes it is. Okay, so the reason that I'm saying this is a little bit odd to do here. What we're doing is we're querying OpenGL and asking it how big the GL array element buffer actually is. And then we're using that to draw. But the fact is we kind of know. Because the GL element array buffer was set up right here. And so the size of it is, you just take this, and so for each of those sizes, it's got 6 numbers, and there's 6 sides, so I guess the size is 36. 36 unsigned shorts. So in bytes, it's 72. So that line basically sets size to 72. Great. But this would take care of it if we added more faces to the cube, for example, up there. It would be really tempting to just track this on the CPU instead, so we don't have to go query the GPU how big the array is before we draw it. But that's not what we're doing. Anyway. Okay, so after that we can call our GL draw elements instance that we talked about earlier, how to do instance drawing, and we go ahead and disable the vertex attribute arrays. I'm not sure that's strictly required. I think it's considered a good practice since you might draw something completely different next. And then we swap buffers so everything shows, and that's that. Okay, so the other big piece in here is this model view matrix, the MVP. And so this is set up by using, so basically you got all these different, these 4 matrices you multiply together and you get one unified MVP. Now calculating on the CPU here is actually faster than calculating on the card, maybe, because we only calculate it once. And we deliver MVP as a complete unit to the card. If we did it on the card, we'd have to do it in each vertex shader. And so, sure, vertex shaders are fast, but we'd have to make a whole bunch more copies of these, see? Be inefficient. Yeah, sure. That's okay. That's funny stuff. Okay, so the model view matrix there is, calling translate here. Translate can move things places, and so we're actually scooching our model 4 units down the z-axis. So if we wanted to also scoot it up, for example, we can say like 2. And now they're higher. Both of them are higher. Okay, so that's the controls here. So in terms of controls for moving it, We use the model view to move the model around, and we got translate call in there right now, which is moving it back forward, but we could do other things to transform it if we wanted to. We could, for example, say GLM scale. I think it's just scale. And so we'll take our initial matrix there, and we'll go ahead and scale it. And so I'm assuming what it wants next is a vec3, maybe a GLM vec3. And this is going to be the new scale, so let's go ahead and make it flat. So we'll say that x1 is just 1, same as normal. Y is, say, 0.2, and z is 1.0, like normal. Okay. There we go. Now it's flat. Okay. Now, the way I just did that, so it makes a complicated collection of functions here. If we look at the parentheses for scale, they surround the whole thing. If we look at the parentheses for translate, they go right there. And so translate is going to return a matrix. And so it comes back from translate, we're going to go ahead and modify this matrix and make it scale. If you look at these functions, they all start like this. You got GLM rotate, and then we go ahead and say we want a GLM map 4, a matrix, 4x4 matrix, and it's going to be initialized to 1.0. And I believe that just initializes the main diagonal of the matrix, gives us kind of a base matrix to start with. And then the next parameter for rotate is how far do we want to rotate it, and what's the y-axis, what points up. So the reason that we give a base matrix to start with here is all these GLM functions sort of assume you have some matrix you're working with, and you're going to apply another transformation to it. And so that's what's going on right there. Okay. So this can be made flat. View 1 sets up for your viewing, and so we're just calling GLM look at in order to generate us an appropriate one. And then with the perspective, so we could change this so that our perspective is weird. 45 degrees here, I believe, is the viewing angle. So if we wanted to be rabbits, for example, we might say like 180. Yeah. It sort of zooms it out a little bit in effect because we got a wider viewing angle, so we're seeing a bigger picture on the same size screen.
Can you put it in 360?
See all the way around us? I don't know.
Those are extremely flat-looking cubes.
Well, I flattened it out up there with that point too.
Gotcha.
Yeah. Oh, I forgot what I missed. 60-degree cameras. I think it ignored us. I don't think we're any further out.
OpenGL on their new
Yeah.
establishing one correction.
Or if you're looking through the sniper rifle scope, make it less. What in the world? Oh, I forgot your mix.
559 is what this is.
359, sure. It's not expecting radians, is it? No, I had 45 before. So it must be fine. Okay, so 359, 359. I think it may have ignored us again. It might be falling to that looks exactly the same as 45.
Yeah.
Yeah. So I'm not sure at what point it goes back to what it normally looks like.
Upside down.
That changed the wrong thing. That shouldn't be able to make it upside down. Yeah, I'm not sure if it took that or not. What do we have before? 45?
Yeah, 200 gram upside down.
Huh, weird. Yeah, it did. Okay. Interesting. So I think large angles there may have unintended effects. But if you're in the normal range, it should be okay. Okay. The aspect ratio there, it's just setting it for our screen height and screen width. It's right on the projector because it's 4:3. I don't think this one actually detects screen height and screen width. No, they're just set right there. So you full screen that on a widescreen monitor, you get something weird. Okay, so that's, well, maybe it is set in resize. Run reshape. Hey, it is. The glove reshape is actually set up correctly. Cool. Okay, good. Okay, so that's how that works. So kind of an overview of that again. Hopefully it makes more sense now, maybe? Okay. Everybody's like, well, maybe. Okay, so the drawing of stuff. So if we wanted to make like a stack of cubes, the traditional way to make a stack of cubes is to just go ahead and change your model view and projection matrix and then go ahead and draw a second one. That's a little bit hard to pull off in this demo in a way, since everything is set up here for the MVP. And then if you want to modify your MVP and go ahead and draw again, it's down there. So I think last time when we did this, what we did is just take all of this on idle stuff and put it down here in the on display. And so at that point, MVP is actually possible. So then if we wanted to recalculate MVP, we just do everything up to there. So go ahead and grab that and so draw everything until we're ready to draw array elements instanced. And then we can do that again and redraw array elements instanced after we've passed out a new MVP. A few of these things can't happen. These things can't be redeclared, for example, here. That's just plain not allowed. And we don't need to redo the angle anyway. Okay, I just did a tab there. And it, I think it actually uses spaces. Okay. Oh, whatever. Good enough. Okay, axis Y doesn't really need to change. So when we've changed set each of these things, we'll go ahead and make the next one somewhere else. The previous one was not very high. This translate here would allow us to take the other one down and take the other one somewhere else, like higher. Then we can go ahead and rotate it the opposite direction. Sure, why not? And we should end up with something else drawn differently. A little build. There we go. So we got cubes rotating, different cubes rotating. It might look better if these ones went twice as fast. There we go. We got cubes rotating faster and rotating slower. They look a little funny up there. Maybe it'd be better if they were down below. We just change that one right there. There we go. And of course, we have the vertex shader duplicating these things. I think it'd be nice if the vertex shader duplicated them both ways, because it currently only does one. Easy enough. It just needs to have 3 indices instead. And then the vertex shader needs to have 3 options here. And so this one will have a 1. And it'll actually be a lot more like that one. But we'll go over by -3. There we go. Now I only changed the GL draw instances in one of those. So right here we're drawing all 3 because we're giving it 3 instances on the vertex shader. But this time when we run the vertex shader, we're only giving it 2.
Huh.
If we wanted to only draw one of them, we can just do that. And sure, the vertex shader supports drawing 3 instances of it, but since we only ran the vertex shader once with instance ID 0, we just get 1.
It's actually kind of cool because all you need to do is make another one that's further down. That's
That goes the other way and is faster or something?
something like that. Further down or further up, one of the two.
Yeah.
Make it do funny things.
Yeah, we probably don't need a GL use program in here. There, that's the block that does it.
Then there's a GL stop use program.
I think you just GL use the next one, but there might be somewhere.
Well, how do you use multiple programs at once?
You don't.
So you just have to add all the shaders to each program you want to use.
Yeah. Go 4 times regular angle.
I love how they're just slowly getting faster and faster.
Yeah. So now it looks like a jump sequence.
It kind of does, you're right.
This turned out to be a lot easier than the jump puzzle I made for Android.
Oh, that took me forever to finish.
I didn't know if you liked mine or not, because everybody's like showing off, they're like, yeah, Seth wrote like all this stuff on mine, and he really got it. And I look at mine, and he's like, I really appreciate the fact to start me back at the beginning, because that would have just been hell to walk back to. And it's like, oh.
I think I spent like half an hour beating your jump puzzle.
I do a lot of them in some of the games I play, so I got really good at it. So like whenever I do, I'm like, yeah, this is super easy. Just like
It's always been something I'm bad at games, actually.
That's okay.
they
He had,
got my face.
he had problems finishing mine too, Ty.
We yours had the thing where you had to find the keys forever.
Mine didn't exactly have that.
So I understand how you feel.
Those platforms though, like the side-to-side ones for me the most trouble. I had to get Jesse to help me.
The question is, was it in first person or was it third person?
First
First person.
That's the problem right there. You should never make a first person platformer.
They're not that hard.
Yeah.
I mean,
Yeah,
I remember Metroid Prime, but I was like, oh, this is never gonna work, and I loved those games.
Well, there's never anything really that hard in them.
And I edited the jump so that you always had a jump, even if you step off the platform, you could still jump. So
Oh, that's right, you had one air jump.
yeah, I gave everybody an error jump. So like, I figured, yeah, this is gonna be super easy.
Wasn't it a single jump every time you left the ground? But then,
No, I had a double jump in there. Oh, you could double jump.
You could. I was trying to beat it without that because I was figuring that that's how you're supposed to do it or something.
No, I put in double jump there because like I figured that
The double jump was on purpose.
That's easy mode.
Yeah.
I did it in one jump for everything, but like
So the last things on here, there's a stack of crates. They didn't bulge this time. That was only part of the lap. I was thinking that we'd have them bulge or whatever. Okay, so in operating systems, somebody was asking for practice problems because there's not like end of chapter problems or anything, especially in this class. So I made up a couple. These aren't graded or anything, but if you feel like you would like to understand this stuff better and
Change the square
you're not
cube
coming
for
up with your own like
rectangular
little puzzles,
diagonal prism.
yeah. So the first one is probably not that bad. To have it go taller and shorter as you go. I mean, you just use the GL scale up that I was using earlier to make them flat, but you have to adjust that parameter and it change as they go. Probably won't take that long. This one would require a little bit of thinking and probably some pencil and paper arranging of vertices and things. But at the end, you'd be good at arranging vertices. It's not really that different than what it is. I mean, it's a cube, and so you just got to add one more face, and so that means opening everything up a bit and putting one more in. Could be a lot of fun, or maybe not. I don't know.
Oh, okay.
So that's a thought.
special cube?
When you say a regular pentagonal prism, my brain doesn't think of, you know, it's got flat top and bottom. It thinks
Oh, yeah.
all the faces have 5 sides and
Oh yeah, all the prisms, like rectangular prism or whatnot, are just like an extruded one.
Okay.
Yeah,
That's what you mean.
Yeah.
Okay.
Make a dodecahedron.
yeah. It's only got.
That's
4
what I was thinking he meant.
It's actually only got 4 more vertices. It's just the vertices are in more difficult spots.
Could you imagine trying to make a dodecahedron though? Because that's what I thought you meant by that.
Oh, okay, yeah, yeah. And then like I've kind of been keeping this upcoming list, so you know it's coming at some point. Okay, cool. That's all I got to say.
Okay.